start now. First, listen to听。傅入云，尹成浩，赵佳琪，崔家园，陆一凡，姚如歌，申浩 ，Great K。Janat, Dean, Tuna, 蔡家峰 Laxmi, okay, on Monday, we just introduced the expressions for the attenuation constant, phase constant, and group velocity, phase velocity, and lambda for various types of the non-magnetic materials. So, first, let's just take a short review. The first one is the for any medium. So any medium. So its attenuation constant R, it has expressions. Complicated. Big square root. And you know epsilon prime epsilon naught over 2. Times square root again. This is the complex, or this is complicated expressions for the expression for the attenuation constant, and for the phase constant, similar expressions. You know that epsilon minus 1 over 2 divided by 1 plus double prime square, here x plus 1, right? And another one is the intrinsic impedance, also has expressions. Node over node minus square root there. 1 minus j times double prime over prime. 1 over and this is the for any medium, and also its phase velocity can be expressed as omega over beta, right? And it's a lambda, its wavelength inside of this material can be expressed as 2 over the phase constant or group velocity over its frequency. So this is for any medium. And we also can simplify these equations when we need to consider, for example, the lossless medium and the low loss medium and conductor. So for the low loss medium, we define H as the imaginary part over the real part to be much smaller than 1, alright? So probably E smaller than 1%, and so the attenuation constant can be expressed as prime divided by lambda node is the wavelength in free space divided by square root, this one, and as a phase constant can be 2 pi prime divided by lambda node also. So the intrinsic impedance expressed as this one, and so because it is a low loss medium, so it can be simplified as this one, and also simply this is low loss. And for lossless medium, it was defined that as conductivity defined as 0. All right. So if the conductivity can be defined as 0, that means the imaginary part should be 0. So the attenuation constant is 0. And the same thing here. Same thing. So same thing. And same thing also. Okay. So for the conductor, here. For the conductor, which means the prime over this one is much larger than 1. All right. So that means the absorption, the attenuation constant can be expressed as. So this equation can be simplified to this one. The phase constant also be define, and also, and the intrinsic impedance, it becomes a complex number. Intrinsic impedance becomes a complex number, so a value. And so this one is the same thing. So this is the expressions for the several parameters for the interaction between the EMV and the media or materials. And there are several conditions: the low loss, the lossless, and the conductor. So here, for today, we're gonna continue our introductions about the power or power density inside of the media. So usually, we defined a Poynting vector. All right. So it can be expressed as via a capital number, a capital character S. It equals the electric field. First time the magnetic field. All right. So it is a time-varying parameter, which means the energy varies with respect to time. And so if we wanted to get just the quantity of this value, so we need to obtain that via get the average or average. Average power density. It can be expressed as the variable of this one, right? First time T star, right? So for this calculation, we can also get the based on this, we can obtain the power flow, right? So because this is the power density, which is defined as the power radiated onto a surface or an aperture with an area of A, for example. So the area aperture area. So we can get the power equals the direction times areas integration. So for surface integration with respect to the aperture. So this one is the power we can obtain, and it can be if usually both vectors are not along the same direction. Maybe they have an angle of theta, for example, and it can be expressed as S times A times cosine theta. All right. So if it's in the surface, and our radiation comes along this direction, so this is X, and this normal vector along this direction, and this is theta, so it can be expressed by such an expression. So if this is just for the regular or any kind of materials, so if we want to simplify it, or if we want to get the expressions for specific mediums, so the first one is basically as we demonstrated previously, the lossless medium. So for the lossless medium, if we define our electric field, it propagates along the theta direction, and it has its electric field is along the x-axis, and also has a y component. So here, and if we wanted to express it as the so the ax and ay should also be the complex quantities, all right? So it's not just a real number because we need to consider its phase components, or because it needs to propagate along the theta direction, so it has a big number. It can be expressed as initial point, the initial value, and also here, initial value times minus. All right, here is real number. And so, if we want to get the the magnitude of this quantity of the electric field, so it can be expressed as really the absolute value can be expressed as square root of E. Stop, all right? So both values together, and so based on this equation, we know that this part, the exponential part, can be erased, all right? So this one it's going to become this square plus y node square, then we have square root like this. So this is the magnitude of the electric field. So for the magnetic field, as we previously know that if, or for the plane wave, the magnetic field is usually in phase with the electric field, all right? So it can be expressed as for the magnitude, it should be the electric field divided by the intrinsic impedance, all right? But they have, according to the right-hand rules, there is vector, their propagation direction is time, electric field, right, divided by the intrinsic impedance, and it can be expressed as 1 over E times minus x y node plus y vector x node. This one, alright? So now it was has fixed with the electric field. This one. So the EM wave can be considered as the sum of both waves, and the combination of them can be, because the EX and HY, right, can be certain of combination, and can also be EY, HX, right? They cannot be parallel to each other. Actually, they should be vertical to each other, right? So this can be the total electromagnetic waves should be the combination of both parts together, and we can regard each one as one kind of the field, of the EM field. And so if we want to calculate back to this one, the average power density, so it should be expressed as this one, right? The cross product. So we substitute this equation and this equation inside of each, we can get the Poynting function, the Poynting vector b expressed as beta 1 over beta, and this value is wrong. It's like x node square plus ey node square, like this one. And then it can be expressed as E like this one, alright? So it becomes this one. So this is the power flow, which usually the power flows along the theta direction, and with every power equal to the sum of the average densities of densities of this one and this one together. And so we need to note that the Poynting vector depends, if we look at this equation, it flows in the theta direction, and it only depends on the intrinsic impedance eta, and also it depends on the electric field E. If we convert that, it can also be depends only on the magnetic field, alright? Because the magnetic field can be conducted by the electric field. So this is for the low loss, the lossless medium. If it is in a lossy medium, so for the lossy medium, what we need to take a review is, for the lossless medium, we can get is the phasor by adding this term, right? So k is the wave number, but in the lossy medium, we has a propagation constant, right? It can be expressed as alpha plus j times beta, and we also has the expressions or the replacement if we wanted to convert our expressions or inductions from the lossless medium to the lossy medium. We just substitute the k by gamma, right, by the propagation constant, and the relationship between both is like what? Minus k squared, right? So that means we need to substitute the jk by the propagation constant gamma, like this way. So now, if we want to express the electric field, when we come back to this equation, so we need to replace this term by gamma, right? So the electric field can be expressed as the same thing, x node plus y node times e to the power minus j chi substituted by gamma times theta. Alright, so it becomes like this term plus this term, e minus alpha theta, e minus j times beta theta. So this is the expressions for the electric field in the lossy medium, and also the same thing as for the magnetic field. So H is running back to this equation, which is divided by the intrinsic impedance. All right. So and it can be like this. So we can also express it like this again. So 1 over eta times minus x no plus y ex no, and e minus alpha theta e minus j times beta. So for this one, for the lossless medium or for a low loss medium, we already consider the intrinsic impedance to be a real number, right? And actually it is a real number. But for the lossy medium, the intrinsic impedance cannot be a real number. So it becomes a complex number. So we use a subscript C, complex, to represent that. The intrinsic impedance now becomes a complex quantity. So now we have the expressions for the electric and magnetic field, and we can also calculate the Poynting vector. All right. So it can be like this one. It equals the part electric field times magnetic field. That's star. And half of H. So we take a cross production, and it can be get the result like it's along data direction, right? Okay. So half of that x node square plus y node square times because it's two parts, so e minus 2 alpha theta. And because this part is imaginary part should be erased or cancelled, and we need this value. So because it becomes a complex number, so it becomes a complex number star, and we need to take the real part of it. So it's like this one. So which means now the expressions not only depends on this one, and it varies or it decays due to the attenuation constant, right? So here, if we wanted to calculate many times, if we can get the attenuation constant alpha from maybe from applications or from our measurements. If we wanted to calculate the magnetic field, the variation of the decay of the magnetic field or the field, the magnitude of the field, it can be only the e to the power minus alpha beta, right? For the magnitude of the field. But for the power, we need to take care it should become 2 times alpha times beta. So remember this part many times is going to be neglected, or it's going to be lost. So let's come back to this expression. So the intrinsic impedance, it becomes a complex number or a complex quantity. That means it can be expressed to be a magnitude, and it also has a figure or an imaginary part. So it can be expressed as this one. Eta c becomes the magnitude of eta c times e to the power j eta. So that's magnitude. Also it has this term. This one. So this is going to be very, very important. If we convert it, if we just wanted to get the real part of it, so get the real part of it by this equation, from this equation. So it becomes real part and 1 over eta c magnitude to the power minus 3. All right, like this one, and so it becomes, this is the real number, real quantity that from it. So the real part of e to the power minus j eta. So it can be 1 over eta c times cosine eta. All right. So the real part of it. So now, when we change the expressions for this quantity, it becomes as theta times half LH. So this term, intrinsic impedance, the magnitude of it. And here is the EX node and EY node. That means the electric field, to the electric field, the square root of the magnitude of it, square of it, and times e to the power 2 minus 2 alpha theta, then times cosine theta, eta. All right. So this is the expressions for the Poynting vector in a lossy medium. So H is related to the electric field, also as impedance intrinsic, and also the attenuation constant of this medium or this material. So if, because this term, the theta eta, it is the the phasor part from the intrinsic impedance. So it is always predetermined, right? So if we can set another term as node, it can be expressed as the E node square, the initial electric field, divided by 2 eta c times cosine theta eta. Then this expression can be simplified as the S node, the initial Poynting vector, times the 2 times alpha eta, right? 2 times alpha beta, 2 here. So that means the Poynting vector only varies due to the attenuation of that medium. So it decays exponentially when it propagates along the theta direction. So this equation is important because we really need to calculate the propagation of the EM waves along over a distance or over a longer distance. Then this term is very important. And here previously we defined a skin depth. So for the skin depth, we defined that the skin depth is is defined as 1 over alpha. All right, so that's because it's for the electric field or the magnetic field is dp. All right, if we take it to the energy or the power, because we have 2 times that, right? Because of the magnitude square root, the square part of calculation between the power and the electric field or the magnetic field. So for our alpha, that means is magnetic, the magnetic field or the electric field decays to this part, right? That's around 137. The 37% is an initial value, but for the power, it becomes 2 alpha. So it decays to the 1 over a square and becomes around 14%. So if we want to say the skin depth or the power decay, or when it propagates over a skin depth, the distance, that means its power decays to the 14% of its initial value. So this is for the power. And for magnetic field or the electric field, we have its units, right? For the electric field, its unit is watt divided by meter. Or for the magnetic field, it also has its own expressions. And for the Poynting vector, it has watts per square meters. And so we have also many other expressions or the units to represent the variation of power. So the most importantly, we already use this dB, all right? The ratio between the detected power and the radiated power, the initial power. So if we have the 2 quantities, the first one is P sub 1. So this is the initial power, all right? And another one is, for example, our detected power or received power. What we really used to get is the attenuation, all right? We calculate the attenuation A by, it can be the attenuation by that one. And also, inversely, is P over C1, right? And also, we can get, for example, the gain. It can be expressed by the P1 over P2, right? So the launched power divided by forwarded power, and it can be expressed by this one. And if we want to express it in the decibel scale, so 10 times 10 P1 over P2. I think most of you should be very familiar with this expression. For the energy variation, so for example, we have the Poynting vector. They were detected by the apertures with the same area, all right? So we just use the Poynting vector. So it's at a position beta, and divided by S, our edge, S energy at the initial point. So it's like this one, the emission for this one, and they are the same. We can get the same expressions for this one. So if in dB or in decibel, for example, decibel 10 times log 10, also, right? 10 times log 10, that means 10 log 10, and it becomes, we come back. So F divided by F no. We only have this term, right? E to the power minus 2 alpha theta. So e to the power 2 alpha theta. Like this one, and as we mentioned previously, minus 2 alpha theta 10 log 10 e, right? So this term can be expressed as 4.34 if calculated. So the totally is minus 8.68 alpha theta. This unit is dB per sometimes can be kilometers or sometimes is per meters. If we calculate this term, the unit of this part. So this is the expressions. This is MP. I'm wrong. Its unit is per meter. So this term, and it can be expressed as minus alpha times theta. So now this alpha is dB per meter, or sometimes dB per kilometer. Actually, it keeps the same. So why we need to get the expressions for both times, for both terms? Because sometimes if we read the data sheet for some devices, they really just give us the value of alpha equals maybe per meter or per centimeter. That's one. And if we want to calculate the signal loss, or we want to just substitute it to the, for example, the first response loss, and we want to take the calculations, we need to know how to convert it to into the logarithmic scale. This is the power loss, and we just consider the expression of the electromagnetic waves when it propagates through from the in a uniform medium or just one medium. But many times we have maybe several layers of mediums that the EM waves should experience, right? So we need to consider the reflection and also the transmission from one medium to another. So now we need to start on the reflection and the transmission of the electromagnetic waves. So firstly or simplistically, we need to usually take the case of the normal instance, right? So for normal instance, and there is reflection and transmission cases for that one. So for a normal instance, we just consider we have two kinds of mediums. And here is interface between both. So this is medium 1, this is medium 2, and the instant wave for normal instant, right? So this is instant wave, and it can propagate through the interface to medium 2, right? So this is instant, and this is transmitted. And also we have reflected, right? So we have reflected. Wait. And so here we usually just consider the plane wave for consideration. So for plane wave, which means its wavefront is lines which is perpendicular to the propagation direction of the instant waves. Right here, we just take, for example, a beam, an EM beam as a ray, or just a line or a ray. So to represent its propagation, and we can simplify our plotting because if we want to replace it as a beam path, it has beam width, then it's going to be very difficult to express it for the oblique instance. So here. Now if we assume the medium M1 its intrinsic impedance is eta 1, for medium 2 its intrinsic impedance is eta 2. So if the first case, if we set the both mediums are lossless media, for lossless media, and they are homogeneous, and they are also the dielectric media. All right. So if we wanted to define the electric field, just the electric field, and we replot this figure like this one in the Cartesian coordinate system, because we wanted to express its electric and magnetic field, right? So this is x-axis, and here is the y-axis. So the theta axis should interrelate across to represent this is theta axis. So y-axis is along is interrelated plane surface along this one. So we define our electric field. So our electric field is along the theta direction. So we define it as EI, the instant electric field, all right? And it propagates along the theta axis, but oppositely. So the wave number, because it's a lossless medium, all right, we use the wave number. So SKI and just a unit vector. So its magnetic field should along which direction? The magnetic field along the x-axis, right? So yeah, along this direction. So this is the magnetic field. So when it is reflected by the interface is the x or y plane, right? So the interface is here. So this is medium 1, this is medium 2. And the reflected field, so for example, first we just consider the electric field. So it propagates along this direction, right? So this is KR, reflected, a unit vector. And its propagation or its electric field is still along the y-axis. And so this time its magnetic field becomes along this direction, alright? So this is HR, reflected electric field. And the transmitted wave, keep the same, right? Everything is along because it's for normal instance, so its propagation direction cannot be changed. It's K T. Superscript on the subscript here. So unit vector, and this is E T, the transmitted electric field, and the magnetic field H. All right. So the expressions like this one. So here, what we need to consider is their properties at the interface layer. The interface layer, right here. So for lossless media, in medium 1, closing to the interface, the total electric field in medium 1 can be expressed as reflected, right? okay, let's take a short review, and I'm gonna come back at 5 minutes. 好了，我们休息一下吧，然后5分钟之后继续。定好来。Okay, the magnetic field The same thing. Each one, in medium one, it has an incident part plus the reflective part, right? So in the medium two, it only has the transmitted part and also the electric field, same thing, transmitted part. So when we wanted to consider the electric and magnetic field. For the electric field, it's always continuous. All right, the electric field, the total electric field, total electric field is continuous across interface, right? Across the boundary or interface. So that means U1 equals E2, right? Is this correct? I think so, right? So for the magnetic field, H1, H2 at the boundary, and they be equal to each other. Why? Can they be equal to each other? They can, but it has condition. It can be alright, but it should under the condition that there is no what? There is no current sources.
It's not so.
Oh. Only when the condition that there is no current source. Signal. So, under the condition that there let me change the sections first. under the condition that there is no current source at the interface. Alright? So both terms should be equal to each other, and the magnetic field is continuous across the boundary also. So when we substitute both expressions inside of H, we need to take care that the E1 equals E2 means our electric field at initial point E node I plus E node R equals E node T. Alright? And the H node I plus or minus. H minus, alright? H minus, they are opposite direction. H node R equals H node T. So the H node magnitude, its magnitude can be expressed as H node divided by intrinsic impedance, right? Minus E node R divided by E medium 1 still. It equals E node T divided by E medium 2. Right? So we have two expressions. And we combine them together, we can get the expressions for E node T divided by E node I and E node R divided by E node I also. Right? Because we have two equations and we can get the expressions for them. And so the first one is E node T over E node I can be expressed by the intrinsic impedances. So 2 eta 2 divided by eta 2 plus eta 1. And this one is eta 2 minus eta 1 divided by eta 2 plus eta 1. I will not show you the details for this conduction, but actually you can check that based on both equations. So this term can be defined as the Fresnel reflection coefficient, alright, rho, very top, is transmission. And this term can be defined as the Fresnel reflection coefficient expressed by rho, alright? So when we look at the equations for them, you can see that the relationship between both terms sometimes or at one time my master student tell me transmission plus reflection equals 1. Is that correct? Is it correct? Transmission plus reflection should be equals 1. Definitely not, alright? Because according to the transmission plus reflection equals 1, that means it is conducted from the energy conservation, alright? The energy conservation means it should be related to the energy of power, right? Instead of electric field or magnetic field, alright? So here is that coefficient. It's not the energy, so we cannot express it by this equation. But if we look at the expressions for both terms, we can get an expression as tau equals 1 plus rho. You get this expression. Alright? So this is for, it is it is just under the assumption that for normal instance, just for normal instance here, and later we're gonna transfer it to the oblique instance, which the expression is gonna be a little bit different. It cannot be like this one. So, if sometimes when we want to, we can sometimes it can be more easier for us to get the maybe the reflection coefficient. Then we can just by this equation to obtain the transmission coefficient, and also and inversely it can be the same thing. So now we get the expressions for the transmission reflection coefficients. We know the intrinsic impedance eta 1 and eta 2. So for lossless medium, the intrinsic impedance can be expressed as eta equals eta node divided by epsilon prime, right? For lossless medium, it has no imaginary part. So for the medium 1, it becomes this one. For medium 2, node divided by node, right? So when we substitute this both the expressions to the to express the reflection and the transmission coefficient, it becomes the like by using this one minus 2 and 1 plus square root. So 2. This is for the reflection coefficient, and for the transmission coefficient, we get the same thing. So the transmission coefficient, we can just 1 plus rho, right? So we get 2 square root 1 prime square root and 1 prime plus square root so 2 prime. So now we can, because sometimes it is not so straightforward for us to analyze the intrinsic impedance, but for the dielectric constant, it is much more formally used to classify or to represent the types of the materials. So the dielectric constant, by using the dielectric constant, we can express the both parameters, which could be more easier for us. We get the analysis on the electric and magnetic field. We should also concentrate on the energy, right? So the Poynting vector again. So for the Poynting vector, for example, in medium 1, because we have 2 layers of mediums, right? So in medium 1, the Poynting vector can be expressed as S1, this one, and that propagates along the direction. So it can be expressed as half of the real part. The electric field in medium 1 first time, the magnetic field in medium 1, again the star, like this one, right? So its expression, when we substitute the expressions previously from these two together, and after the reduction, I will not show the details, but it can be expressed as along the theta direction and eta 1 and over E node I instance square times 1 minus rho square root square, this one. So this is the expressions for the Poynting vector in medium 1. So we can see we have 2 terms, right? The first term is 1. The second term is rho square. So we can get this expression as 2 terms, S1 I incident and plus the the S1 reflected, right? Because rho relates to the reflection coefficient, so its absolute value, square of its absolute value, and we use this term, reflected energy, to represent it. So now this term can be expressed as minus theta times 2 theta 1 and pi squared. Right? And this term is theta and 2 theta 1 in the pi squared and times rho squared. So you can see both terms propagate oppositely, right? One is along always along the theta direction, the theta axis, but this one is opposite to its direction. This is along its direction. So along its direction. So that means one is the instantaneous energy, another term is reflected energy, right? So and the difference between both is the reflection coefficient, rho squared, absolute rho squared, right? So that means the absolute rho squared can represent the reflectivity, right? So it can be expressed as the reflectivity. We already used the capital gamma to represent it. And also, when we express the Poynting vector in the second medium, there is only a transmitted term, right? So it can be to theta cross h to theta star, like this one, and it can be expressed as also minus opposite along the theta direction, the whole square, times 2 theta 2 e node I squared. So the final expression is like this one. Okay, I'm not showing you the conduction on that one. Here we can see we have the whole square term, which represent to the transmittivity. Later we're going to show that. And from here, when we compare both terms, the S1 and S2, both should equal to each other, right? The energy flows from medium 1 to medium 2. So S1 theta should equal to S2 theta, right? And then we can get the expressions on the terms. Of course, 1 minus rho square over eta 1. So this is for a lossless medium. There is no energy, for example, absorption inside of the medium, and the expressions for the reflection and the transmission coefficient can also be expressed like this equation, which is related to the intrinsic impedance of both mediums. And so, yeah, this is the for lossless medium. Lossless medium. Actually, as we mentioned, if if we want to convert it to the lossy medium, for lossy medium, we can repeat our conduction by replacing, as we mentioned here, by replacing this term, by taking this term, by replacing the Jk by the propagation constant, and then we can conduct the same procedure like this one. So this would not express the format of these equations, but it's gonna change the details of it. And here until now, we just consider for the normal instance, right? So if we're going to consider the oblique instance, so for the oblique instance, the first thing we need to consider is, for oblique instance, what we really need to use the theory or the law, Snell's law, right? So if we have two mediums, also medium 1 and medium 2, and we have instance wave, which is instant wave. So this is the normal line, right? Normal, we have instant. This one. So instant wave, we use I to express it, and its instant angle is theta 1, and the reflected angle, reflected is this direction, is theta 1 prime, right? Clearly, and the refracted beam, and this angle is theta 2. It's refracted beams. Presented. Okay. Yes. So according to Snell's law, theta 1 should equal to theta 1 prime. Alright? And also, this is Snell's law for reflection, and the Snell's law for reflection. Snell's law for reflection. And also we have Snell's law for refraction, right? Sin theta 2 over sin theta 1. It is related to the group velocity mu p2 over mu p1. So this is the phase velocity, and it is related to the dielectric constant, epsilon 1 prime over epsilon 2 prime, right? So this is the Snell's law for refraction. So now Snell's law of reflection states that the angle of instance equals to the angle of reflection, right? And the angle of refraction with respect to the angle of reflection for the instance follows this equation. So we have both equations previously. Another term is the so previously we considered that for the material, for any medium, any kinds of medium, we use the dielectric constant or the permittivity and permeability and conductivity to characterize them, right? So another thing we also need to consider is the what sometimes we wanted to represent a kind of material. We use the index of refraction. Alright? We use character n to represent it. Alright? So the what? the refraction index or index of refraction is usually defined as the ratio of what? And it's usually defined as the ratio should be related to both kinds of materials. All right, the ratio of the light speed of them with respect to in free space, with respect to the phase velocity. Also, the light speed in free space equals to the phase velocity, right? And the phase velocity inside the medium. So that means the index of refraction, it is a term or a quantity with respect to free space, right? Because that's why we defined the index of refraction in air usually equals to 1, because it's just ratio. All right, it's not an absolute quantity. So n can be expressed like this one. So it equals the speed of light. It should be equals mu naught epsilon naught. All right, and the group velocity should be mu naught epsilon naught, and also the dielectric constant, the real part of it, of the material. So what can be expressed as square root of epsilon prime, right? So really, when we want to get the index of refraction, we can conduct it from the values of the dielectric constant. Oppositely, we know the refractive index. We can also get the dielectric constant, but only the real part of it, right? So that's because we, for the imaginary part, you know that it only affects the our loss, right? That's a loss factor. So for the refraction, we can just consider the real part of it. So now, when we come back to the Fresnel's law of refraction, it can be conducted as a 1 over n2, right? So I think you guys should be very familiar with this equation. It's related to the refraction index or the refractive index. So So basically, because the refractive index or the index of refraction, I think is a little bit not so physical term. So in physics, we really use this term to represent the which quantity of the material. Ready? The density, right? Sometimes, if we have two kinds of materials. For example, if its refractive index is much larger, then we can define it as dense. It's more dense or large. And so if we have these two materials, 1 and 2, so if and its refractive index N1 and N2, so if 2 is more dense than 1, that means N2 is larger than N1, alright? So when N2 is larger than N1, that means theta 2 is smaller than theta 1, right? We are according to this equation. N2 is larger than N1, that means theta 2 is smaller than theta 1. So that means the refracted line or beam is much closer to the normal line, alright? So if this is for closer to the normal line, we define it as inward refraction. Sometimes N2 is smaller than 1, corresponds to theta 2 is larger than theta 1, right? It becomes larger than theta 1, this one. So this is theta 2. So this is because the refracted ray of line is farther away than the incident line, corresponds to the normal instance of the normal line. So this we can define it outward refraction. So if, and this is condition 1, this is condition 2. So for condition 3, if we still take this into smaller than n1, and when we increase our, because this is for the outward refraction, if we increase our incident angle theta 1, increase it, that means n2, theta 2 also increases, right? And when theta 2 reaches to 90 degrees, that means there is no transmission inside of the minimum 2. Alright? It only follows the surface or the interface or the boundary between both layers. And so this time, the angle theta 1, I think you should know the angle of theta 1 is, it has a new name called critical angle, right? Critical angle, and which corresponds to theta 2 equals 90 degrees. And when we substitute this one to this equation, that means 1 over sin theta c equals n1 over n2, and get the critical angle, alright? So I think you should very familiar with this angle. And but how the wave, the refracted wave course, because now it only propagates along the surface, it is called a surface wave. And this wave is non-uniform, and so now this phenomenon is called what? Total reflection. Reflection. So this is for the just consider on the Snell's law. Then terms. I need to hurry up. So now let's consider the oblique incidence again. So this is interface or boundary x-axis, and this is boundary. This is not boundary. This is the theta axis, and our y-axis enters the page surface, right? So we have an electric field comes in this direction, and it is reflected in this direction and transmitted along this direction here. So we still define our electric field, which enters along the y-axis, and it propagates. Change the color. So it propagates along this direction, and we define it as the wave number, right? So, and this one is Ki, this one is Kr, right? And the electric field is still enters. And its what? Its magnetic field should be along this direction, right? It's perpendicular to the Ki and E. So this is the electric field I, and this one is HI also. And this side, the same thing, the reflected HR and the reflected electric field ER. So, and the same thing for the side, the medium 2, the electric field ER, the refracted part, and also the magnetic field this direction HR. So here we have the two kinds of classifications, right? Which depends on the direction of the electric field with respect to the surface. All right. So, for example, we have the polarizations. The definition of the polarizations: the horizontal polarization, and the vertical polarization. All right. We also have parallel polarization and perpendicular polarization. Right? We have two kinds of classifications for the polarization. So first one, for horizontal versus vertical polarization, we define that when the vertical horizontal polarization means if the electric field, the direction of the electric field is parallel to the surface, not the instant surface, just the surface. The surface, for example, if we want to for our, for example, for the radar detection, if we have our radar signals related to the surface of the object, all right? The surface of object for this dialogue is X or Y plane. So our electric field enters the X or theta plane, right? So it is parallel to the X or Y plane. So it becomes a horizontal polarization. But if we consider the instance plane, the instance plane is it contains the normal line and it's determined by the normal line and the instance line. All right. So it should be the X or theta plane. All right. So we can see here our electric field enters this plane, which means it is vertical to this plane. All right. So under some conditions, it is defined as perpendicular polarization. So it has two kinds of classifications. Along this classification, it can be a horizontal polarization, and which with respect to the vertical polarization. And under such classifications, it can be a perpendicular polarization with respect to the parallel polarization. So sometimes when you read some references, you should know there are two kinds of classifications, and we should be careful about that. So this is the classifications for the polarization. And if we wanted to express the electric field as a horizontal polarization. So for horizontal polarization, which means its electric field only along the y-axis, all right? So we define it as EH, horizontal polarization. H, 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 EH, H. horizontal polarization. So we can EHI instead of the electric field can be only along the y-axis, and is initial value as in each node I, and it has E minus J for lossless medium. Lossless medium minus K, alright, we use key number times propagation direction. Previously, we set zeta, alright, because it propagates along the zeta axis, but here it is not, right? It follows this direction. This direction can be expressed to two parts. One part along the x-axis, another part along the zeta axis. So we just consider it as dB K times R. Okay? So R can be expressed as a unit vector along the xo zeta plane, in the xo zeta plane. So for xo zeta plane, it can be expressed as x cosine theta, cosine theta 1, right? So x. This is theta 1. So it can be the x sin theta 1 plus y theta cosine theta 1. So x sin theta 1 and y cosine theta 1. If we define it along this direction, then here is minus, right? Minus value. So, but for our expressions for the key part, k is always along the x-axis, and theta axis can be divided into both sides. So the number of k, so h is can be divided into two parts. One is along the x-axis, and one side is along the theta axis. So for the x-axis, it becomes what? It can be as t number as x unit, and along the this is theta, right? So x and minus, sorry, this one, and the minus theta, okay, theta. So we take this product and we can get the expressions for the electric field and the magnetic field. So the electric field substitute both terms together, get this one, and the magnetic field, it equals the HI again divided by eta 1, but we need to take care of the term, right? The curve part of it. So that means its direction is going to be a little bit different. with respect to the electric field. So I wanted to get the expressions for these questions. Looks like we do not have enough time. So next week we're gonna just proceed this part quickly, and then we're gonna start a new chapter for this one. So okay, I think we are done today. 那我们今天就先结束了，然后呢，下周的话我们再稍微的延伸一点，开始新的内容。But I cannot tell you which way to go. Guys, on this side. Let me see. You can see here. This one. Your number,